So before we begin today, I just want to make a couple of announcements. I've had a few requests about additional review material, and I'm working on talking to Professor Schulte to get some of his old exams. My anticipation is that I can actually send something out, a second practice exam tonight. So we'll say most likely. Practice exam number 2, I'll send out tonight. Along with solutions to practice exam 1, which was from 2018, I think. Right, so, also related to the exam, remember that exam 1 is this Thursday. I don't think I've said this yet, which I apologize for. It'll be in class, okay? It's 1 hour long. And that hour will be the last hour of class, 2:10 to 3:10. We'll take last minute questions for the first 40 minutes. Okay? So, something of a review session in the beginning of class. Okay? Oh, and of course, what this means is that if you intend to come into class, you should bring a device to submit your work. Otherwise, I would say just stay home and have your computer or phone, however you want to, just take pictures and upload it to Canvas. Okay? So, and I should say this. You'll have 15 minutes of uploading time. Which, of course, implies you must submit your work by 3:25. Okay, now I understand. Oh, it seems like we have a few questions here. Do we need to physically be in class for the exam? Oh, no. Yeah, right. So Kina asked an important question. This thing I said, practice exam 2, this is practice for the exam on Thursday. It's not practice for exam 2. Why don't we say this? Okay? Yeah, good. So the other thing I wanted to say related to the exam is for people in different time zones, of course, I acknowledge that. I'll send you a different form for the exam. Equivalent difficulty, different questions. Okay? So, and I'll be in contact with you later tonight about that, if you're in a different time zone. Okay? Good. So, so Keenan asked if you could get the solutions at the same time as the practice exam. I think it's worthwhile that you try them without. I'm going to send the solutions to practice exam A tonight, and then I'll send the solutions out for practice exam B tomorrow, like probably before class. But just take an hour if you can, or take some time and try your best to do them. I think, you know, this happened to me when I was an undergraduate. If I waited until I had the solutions to go over review material for exams, I found that I was less prepared overall. It's because digesting mathematics requires you to struggle often. So I think, unless you've already digested it, but I think the struggle is important. Okay? Good. So any other questions about exam logistics? Okay. So on to homework from yesterday. So I realized I made a mistake. I assigned you question 3.5. But really, a lot of those, it helps to know what we're going to talk about today from chapter 3. We didn't finish chapter 3 yet. So, let me just say, we'll revisit question 3.5 from the homework tomorrow. Okay? I expect that there are a lot of questions related to some parts of 3.5, but everything will be much clearer after today's lecture. Okay? Right. Oh, I guess one other logistical thing I should say is that I'm not going to assign any homework at the end of today. We're just going to go over all the questions from the practice exams. Okay? So, tomorrow, homework is just to try practice exams. Okay, and then at the beginning of class tomorrow, we might even spend more time than just the usual half hour, just to get everybody ready. Okay, so accepting question 3.5 from yesterday's homework assignment, what questions do we have?
3.2.
3.2, okay, yeah. So let me remind you what 3.2 says from the textbook. We're asked to prove that tau sub a comma b times sigma sub p times tau sub a comma b inverse is equal to sigma sub q for the following scenario, where we have the point q is equal to the image under tau sub a comma b of p. Okay, so, okay, yeah, we'll get to 3.6 after we discuss this, Keenan. Good. Okay, so now, does anybody have a proposed angle of attack here? What might we do to start to address this problem?
I just started at an arbitrary point.
Start at an arbitrary point. So you want to take like a point R.
I know, like, let's get an XY pair.
Yeah, okay.
So, yeah.
Okay, and then how should we
I basically just assigned values to the points it gave us.
Okay, this is the completely analytic way to approach this problem. is you assign labels for the coordinates of A, B, P, and Q, and just churn out the computation. That's definitely a way to go.
Only like 3 lines, it's over.
It's not so bad. Right, so let's make a note of that. In fact, one valid way to proceed is completely analytically. That is, name all coordinates of all points and use the definitions of the equations of tau sub A comma B and sigma sub P, sigma sub Q to make this computation. Okay, so this, I'm glad you said this because this is yet another example of just a computation constituting a proof. Okay, but let's proceed synthetically. Or rather, I should say, a mixture of synthetically and using the results of transformation geometry that we've developed. Just to see how this more nuanced way might go. This is definitely correct, right? If you submit work for this type of problem that is just entirely analytic, that's 100% acceptable. But I think everybody is able to do that. So let's see an alternate way to do that. Okay. Okay, so here's a kind of subjective question. What was our main result yesterday? Alternatively, what was our main result?
Do you mean after we define half turns?
After we define half turns, yeah.
The idea of equating specific half turns regarding midpoints with the translation.
Yeah, we developed this correspondence between half turns and translations, right? Namely, that the product of any two half turns is a translation. Okay, so let's just say that first. Call the product of any two half turns is a translation. And the other part of this, any translation can be written as a product of two half turns. Two half turns. Okay, so now, if I look at the left-hand side of my proposed equality. Of course, since tau sub a comma b is a translation, its inverse must be a translation because of what I asked you to prove last night, that translations form a group. And so the inverse must be a translation as well. Okay, so what this means, so the left-hand side, tau sub a comma b, sigma sub p, tau inverse a comma b, is the product of 5 half-terms. Now, what does that tell us? Well, what that tells us is that this entire product itself must be a half-turn. Because a translation followed by a half-turn is a half-turn. And a half-turn followed by a translation is a half-turn. Okay? Of course, it's not, yeah. So we'll state that in greater detail when we begin today's lecture. We'll reiterate that in more concrete detail. We basically said it yesterday. Okay? It's a consequence of this, this theorem that we proved that the product of 2 half-turns is a translation and vice versa. But, so, let me just, for now, say this. This implies that the whole product is a half-turn. Okay, so, in this case, how do we show that, okay, we've made a significant step, right? We've shown that both sides of this are half-turns. How do we guarantee that they're the same half-turn? What is it that characterizes a half-turn? The fixed point. Right? So on the right-hand side, sigma sub q, we know that q is the fixed point. So if we want this half-turn to be equal to this half-turn, we had better have that the fixed point is q. Remember, the fixed point is unique. That's the first thing we said about when we characterized all the basic properties of half-turns. Okay? So, to show that tau sub a comma b, sigma p, tau sub a comma b inverse is equal to sigma sub q, we must show that q is the fixed point of both sides. So in other words, we just evaluate this on q. Okay? So tau sub a comma b times sigma p times tau sub a comma b inverse q. Okay, what is tau inverse sub a comma b of q? P, yeah, it's just, by our hypothesis, the inverse of tau sub a comma b has to make this p. Good. Oh, now, what's sigma of p? It's just p, yeah. And now by hypothesis again, we get q. Okay? So, just a word of don't want to say advice, but these are equally valid ways to solve this problem, analytically or using the theorems that we've proven. Personally, I tend to favor this kind of, like if I'm making a deduction, just because I'm really error prone at computations. I feel like I always miss a negative sign or add two numbers incorrectly. But it's completely a matter of taste, okay? Again, this computation that we outlined here constitutes a proof, okay? Okay, good. So, Keenan asked that we talk about number 3.6. Next. And what does 3.6 say? So, this question is weirdly worded. I'm going to write it in a slightly different equivalent way. Okay? 3.6. Let's say instead, if some transformation alpha of x comma y is equal to, what do we have here? Negative x plus 3, comma, negative y minus 8. Express alpha as one of the types of transformations we've studied so far. Right? Are the equations for which transformation? So in the book originally it says if x prime is equal to negative x plus 3 and y prime is equal to negative y minus 8. These are the equations of which transformation. That's kind of a misleading phrasing, I feel like, because it's like, oh, it's the transformation that has these equations. That's trivially satisfies what exactly the book asks, right? So really what we want here is express this as a translation or a half turn or some such like this. Okay, so with that in mind, what do we think? Say that one more time.
It's the typical half turn formula.
Okay, yeah, so notice we have negative signs in front of our x and y, and our input is just x and y. So that is to say, we might guess that we can express this as a half turn, right? Okay. So since we have negative x and negative y in the output of alpha, our first guess might be that alpha is some half turn. And in fact, what is the other requirement for the equation of a half turn? Yes. So I mean, if we want to, again, see, even the way I rewrote it, it's somewhat ambiguous. But if I want to say exactly what half turn this is, we should say what the fixed point is.
Oh, yeah, it could have been zero, you wouldn't need or require any actual equation, right?
Well, so remember, what's the general equation for
Right.
half turn?
Yeah.
It's
Plus 2 times the point value for HK.
Yeah, both these constant terms, which are added, are 2 times the coordinates of the fixed point. So if I want to say alpha is equal to sigma sub p for some point p, if I really want to characterize alpha as a specific transformation that we've studied before, I should say exactly what p is. So what is p here?
1.5 negative 4.
Yeah, exactly. Where p is equal to 3 halves, comma, negative 4. Yeah, good. And really just testing to see if you remember the definition of what a half turn is. Not the definition, but the general form of the equation for a half turn. Okay, now, 3.6 also asks, secondly, what are the equations of tau inverse of sub s comma t, where if s is equal to a comma b, a comma c, and t is equal to g comma h. Okay, so first of all, what is the general form for the equation of any translation?
X plus and 1 minus b.
Yeah,
1 minus b again.
yes, it's x plus a. So not disregarding the notation that we've written down here. In general, it's x plus a plus a comma y plus b for 2 numbers a and b. Now, how do we determine those constants, a and b? We have to use the coordinates of s and t. Okay, so let's do this step by step. First of all, tau of s sub s comma t, which of course is not what we're asked for, but let's compute this first anyway. So if I want to go from the point S to the point T, what should my constants be here?
T subtract us.
Yeah, exactly. We'll take the final point and subtract the initial point. Good. So this is G minus A, and in our second coordinate we get H minus C. Right? And the way you check that, just plug S into this, and you get T out. Okay? So, now, remember, if you know what a transformation does to a single point, you know what it does to every point. And furthermore, we know what it must do to, well, how that describes the inverse of tau. Yeah. Okay, yeah, sorry, I missed some questions here, but Ryan, you're okay about the coordinates for P? Thank you, Keenan, for answering that. Good. Good, okay, so now the inverse, here's the blend of synthetic and analytic reasoning. The inverse of tau sub s comma t has to take t to s, right? typically, we just interchange the roles of T and S. We start at T and go to S. Okay? So that means just flip what's positive and negative in each of our constants.
You get the same answer during the whole U and V substitution, subtracting.
Yeah,
Yeah.
that's right. Yeah, you can go, again, completely analytically. But just recognizing that the inverse of tau sub S comma T must take T to S. I feel like that's just a tiny bit faster. Okay, so what does this give us? It gives us X plus A minus G, comma, Y plus C minus H. I'll just say, since this translation takes T to S. Okay, so I should point out here that I don't think we said this explicitly, but we've actually just reasoned out a general formula for the inverse of a translation, right? If a translation is the unique translation that takes S to T, then the inverse of that translation that takes S to T is the translation that takes T to S. Okay? In fact, in general, the inverse translation that takes S to T is just the translation that takes T to S. Okay? Okay, good. So, what else do we think here? Should we move on to discussing the group of transformations? Or are there other questions before we do that?
Literally one question we haven't covered.
I'm sorry?
There's only one question we haven't talked about.
Yeah, that's right. Do we want to, this is my question, do we want to take the time to go through 3.7 together, or would we rather just, how does everybody feel about that? If even one person wants to see it, we should do it. Okay, great, yes. So we'll do 3.7. Okay, so, again, I may recall exactly what it says. So, it asks you to prove or disprove. Sigma sub p times tau sub a comma b times sigma sub p is equal to tau sub c comma d. Where c is equal to sigma sub p of a, and d is equal to sigma sub p of b. Okay, so first of all, or rather I should say, who thinks this is true and who thinks this is false? Okay, we have one true. Anybody else think otherwise? Not seeing any other responses. So why is this true?
I did just the analytic approach where you apply the transformation on the point x, y, and then showed that.
So again, here we can label a point, and analytically, show the left and right hand sides. Have the same equation. Perfectly acceptable. Nothing wrong with that. Let's reason synthetically / transformationally just to see the alternative approach. Okay? So, or you could also note that, remember, we characterized half turns as involutive. Every half turn is an involution. Right? Okay? So, sigma sub p is an involution. Like all half turns. So this implies that since C equals sigma sub p of A, what this tells us is that sigma sub p of C is equal to sigma sub p of sigma sub p of A, which is just A. Okay? That's coming from here. Okay, so in that case, then we know that tau sub A comma B is a product of half turns, of two half turns, right? All translations can be written as a product of two half turns. Meaning the left hand side is a product of four half turns. Of four half turns. Which implies is a translation. Why does this imply that this is a translation?
Because it was four half turns, it's also the two pairs of half turns, which is the product of translations, which is a translation.
Right, because translations are a group, right? So if I just make up some notation, let's say tau of A comma B is equal to sigma sub S times sigma of T for two half turns, right? Then what I get is I get sigma P, sigma S, sigma T, sigma P. And I get sigma P times sigma S times sigma T, sigma P. Both of these are translations, and translations are a group. So the product of two translations is a translation. Okay? So, now, all we have to show, great, we got that both sides of this are translations. Now what we have to show is that this translation on the left-hand side takes C to D, just like the translation on the right-hand side. Because remember, we used the fact that for any pair of points, there's a unique translation that takes one point to the other. So in order for these to be equal, they have to both satisfy that, since that's the way tau is defined on the right here. Okay, so now check that sigma sub p, tau sub a comma b, sigma sub p takes c to d. Well, now I can just evaluate. Sigma p, tau of a comma b, sigma p of c, right? Which we deduced here was equal to a. Sigma p, tau of a comma b of a. Okay, so tau of a comma b of a is just b, right? That's from the definition of tau sub a comma b. I get sigma sub p of b. And now I go back to my hypothesis. Sigma sub p of b is just d. So it turns out it was true after all. Now, on that one, I can't necessarily argue that it was faster to reason synthetically.
The analytic approach is really long on that one though. You had like 8 coordinate names.
Yeah, so, you know, it's really a matter of taste, like I said before. But I hope that over time, these quick deductions that we're making in between become more natural. They'll become like second nature. Okay? Okay. So, good. Let's just quickly discuss why the set of all transformations translations is a group. Okay? Okay. Did anybody work on this at home last night? Okay, good. How should I start?
Property you want to show?
Yeah, that's what I'm asking you. What should we?
Iota is a translation.
That's very young.
Oh, sorry, said it.
Iota is a translation.
Iota is a translation. Yeah, good. Identity. Iota is a translation. Namely, tau sub p comma p of x, y is just equal to x plus 0, comma, y plus 0, iota of x, comma, y. I think we discussed that when we defined translations. Good. So, associativity, we know, we've discussed that at length as well, that any set of transformations has the associative property. So, really all we're concerned with is closure and inverses.
Inverse we've talked about this lecture already.
Yeah, so in doing the homework, we already said what the inverse of a translation is, but I didn't give you the analytic formula. So I think that's probably worth saying, especially if we have people that prefer to do analytic proofs, then we should say this outright. Okay, so okay, what we already showed is that the inverse of tau sub A comma B is tau sub B comma A. With equation, what is the equation of tau sub B comma A of x, y? Well, let's put coordinates on A and B with A equal to, I don't know, let's say C comma D, and D equal to E comma F. Then what do I get for the inverse? Well, actually, I think we did say this explicitly, didn't we? We just multiplied the constants by negative, right? Okay, good. Sorry, I'm repeating myself. Is given by x plus E minus C comma y plus D minus F, right? No, F minus D. Okay. Just to re-emphasize. Okay.
That's good, it should be subtracted, so
Oh, sorry.
for that, never seen.
See, this is why I try to do the least things analytically. Okay, good. All right. So, how about closure?
Custom that analytically.
Yeah, sure. So yeah, I mean, let's see, what should we say here? Yeah, let's let, this time I'll follow my notes, so I'll be less prone to make a mistake. Let's let S be the point A comma B, T be the point C comma D, and R be the point A plus C comma B plus D. Then what do we have? If we take the product of tau sub O comma T, the origin, and tau sub O comma S. Oh, yeah, that's right. Yeah, good. Of x comma y. So I get tau of O comma T of x plus A comma y plus B is equal to x plus A plus C comma y plus B plus D is tau sub O comma R of x comma y. Okay, so the set of transformations forms a group. I'm sorry, set of translations forms a group. Now, I actually asked you to say more, and the fact is that the set of translations forms an abelian group. Okay? In fact, remember, we denote the set of all translations by this script T. Forms an abelian group. Why is this? And what does abelian mean again?
You have to prove commutativity.
That the product is commutative. If you take the product of any two translations, you can switch the order and you get the same thing. Okay? So, how do we see this? Well, it stems from the fact that addition of real numbers is commutative.
You can also deal with vectors, right? And just use that geometrically. I mean, it still stems from addition of real numbers, but
Yeah. It's just, if I have some point, A, C, and B, D, then I can switch the order of what's being added in here. Okay? So, this implies that tau sub O comma S is, times tau sub O comma T is equal to tau sub O comma T times tau sub O comma S. Okay, so for each application of a translation, I'm just adding a number to my input vector. I can switch the order in which I add those numbers. And then you get the same answer. Okay? Okay. Good. So, with that, let's wrap up everything that we can say about half-turns. And I'll give you a preview here. It may seem like we are embarking on a never-ending task because we spent a lot of time yesterday talking about the product of two half-turns and characterizing the fact that that was in fact a translation. Now we're going to talk about the product of three half-turns. But that's it. We won't go to 4, 5. From there we can deduce the fact that we already used a couple times from the homework that an even number of half-turns turns into a translation. And an odd number of half-turns is in fact a half-turn. And then our big conclusion for today is the fact that the set of all half-turns don't form a group in their own right. But if you throw in the translations, you get a group. So I made this mysterious comment when we did our brief discussion of group theory that not every subset of a group is a subgroup. But you can always generate a subgroup given a subset by taking all products of that set that you're considering. And so it turns out the consequence of what I just said about characterizing even and odd numbers of products of half-turns means that translations are the only additional thing you get besides half-turns. So all the half-turns and translations put together form a group. Okay, and this is the first example that we've seen where we consider a set of transformations that does not form a group on its own. But because we have such a nice characterization of products of half-turns, we are able to make some coherent, useful definition of the group generated by them. Okay? Okay. So, let's see. Okay. So, turns. Continued. Product of 3 half turns is again a half turn. And in particular, if we have P, Q, and R non-collinear, then sigma sub R times sigma sub Q times sigma sub P is equal to sigma sub S, where S is chosen. So that the quadrilateral is a parallelogram. Okay, so again, we come up with this kind of interesting relationship between classifying whether a quadrilateral is a parallelogram and some condition on a collection of transformations, in this case in particular half turns. Okay? So let's see here. So let's prove the first part of this entirely analytically. Okay? So and typically when we do things analytically, the first thing we'll always do is put some labels on our points that we're concerned with. Okay, so let's suppose P is equal to A comma B. Q is equal to C comma D. And R is equal to E comma F. And then we're going to set S equal to A minus C plus E, comma, B minus D plus F. Okay? And now I'll just take some point x comma y and evaluate it on this triple product. Okay? So let's see, sigma sub R, sigma sub Q, sigma sub P of x comma y is equal to, negative x plus 2a comma negative y plus 2b. Forgot all my other half turns, sorry. Negative x plus 2a, negative y plus 2b. Okay, of negative x plus 2a plus 2c, comma, negative y plus 2b plus 2d. And then finally, we get, so negative is positive, negative is positive. Then when I apply sigma sub r, I get another negative, right? So I get negative x minus 2a plus 2c plus 2e, comma, negative y minus 2b plus 2d, all plus 2f, which of course is just equal to negative x plus 2 times a minus c plus e, comma, negative y plus 2 times b minus d plus f, which, because of the definition I made of s, is just sigma sub s of x comma y. Okay, so the important thing to notice here is that I've just given labels to p, q, and r. And then I made a definition of s based on those labels, right? Okay, so, right. Now, what about the second half of this? Of course, if p, q, and r are not collinear, what does that say about them?
You said parallel.
Sorry?
You said they're not
Yeah, if we assume that p, q, and r are not collinear, what does that tell us about them?
Lateral and arbitrary fourth point.
There's only one line that goes through, like, only 2 of the points at a time. And like, the third point will always be left out.
Yeah, that's a good, these are all, everything everybody said so far is correct.
We can generate a fourth point that creates a parallelogram.
Yeah, there's a unique point that makes a parallelogram. That's not true, it's not unique. There's a point, you can find a point that makes a parallelogram, right? And namely, so, okay, let's say, I want to reproduce this diagram. So let's take the point P equal to A, comma B is here, and we'll take Q equal to C, comma D here, and we'll take R equal to E, comma F here. What I was looking for when I asked you what can you say about 3 non-collinear points is that they span a triangle. Okay, yeah, but everybody said a lot of correct things, which is good. But yeah, so there's a couple different ways to make parallelograms out of that. We've chosen a particular way by our choice of positive and negative signs here. Okay? So that is to say, this is S. The A minus C plus E, comma, B minus D plus F. Okay? Yeah. Okay, congruent sides and equal angles. Okay, so this picture doesn't exactly constitute a proof, but I think that's all I want to say about it.
Yeah, to the internet, you can get both of those equations just by subtracting the coordinates.
Yeah, right. It's just coordinate arithmetic. Yet again. Okay. Okay. So this what I said was the main fact from last time, that we can express a translation as a product of half-turns, and that any the product of any half-turns must be a translation as well. So this allows us to want to say something more succinct based on that fact.
Like translation factor?
Well, so it's about a unique way to determine a point, knowing 3 points. Okay, so let me just tell you what the statement is. There's another theorem about half-turns. If we know any 3 of the not necessarily distinct 4 points, A, B, C, and D. The 4th point is uniquely determined by the equation tau sub A comma B is equal to sigma sub C times sigma sub D. Okay? So I want to emphasize again, this allows us to have a completely synthetic statement that is just expressed as a condition in terms of transformations.
And what about D, or
What about D?
it just says unique?
Is uniquely determined.
Like, yeah, like, so that point is unique.
Yeah, yeah. Right, so that is to say, you could know any 3 of these 4. And then this equation uniquely determines the 4. Is there something?
There's another criteria here, right?
No,
Like, that make a parallelogram, or?
no, they're not even distinct necessarily.
Really close.
So this is giving you an effective condition for how to factor a translation into half-turns.
Okay.
Or if you have a couple half-turns, you can get the points that it goes to, the points that the unique pair of points that the translation takes one to the other of. I still didn't say that right.
So it lets us undo the composition of those two, basically.
I'm sorry.
Well, yeah, okay. It lets us separate the composition of those two half-turns. We don't have translation.
Yeah. Okay? So this is just the effective condition for how to write down an explicit factorization of tau, or to come up with the tau given. Okay?
So like one of those 4 be unknown to us?
Yeah, exactly. One of A, B, C, and D will be not known to us.
Okay.
And then this equation uniquely determines that 4th one. Okay? Is everyone okay with that? Okay. So, I think in the course of the proof,
Yeah,
things will become more clear in case they're not totally clear just yet. So, let's first assume that we know A and B. Oh, sorry. Let's first assume that we know C and D. And also A. Okay? So this is actually going to take 4 cases. We'll assume that we know all choices of 3 points that we could, and then show that the other one is uniquely determined by this equation. Okay? So, then set here, sigma sub C, sigma sub D of A equal to B. Then sigma sub C, sigma sub D must be the unique translation taking A to B. This is the easy direction, okay? So, and then just to be fully explicit, assume now we know C, D, and B. Then what we'll do is we'll set sigma sub C, sigma sub D inverse of B equal to A. Okay, then we have the same result. We know that A is uniquely determined. Let me say it explicitly. Then sigma C, sigma D inverse, which is equal to tau sub A comma B inverse, which is equal to tau of B comma A, is the unique translation taking B to A, and so tau of A comma B equal to sigma C, sigma D inverse is the unique translation taking A to B. Okay? Again, not so bad. Now it takes a little more work if we assume that we know A and B and one of C or D. Let's see that now. D. And now, and we'll let the midpoint of the line segment AB be capital M. Okay, so right. Then, by yesterday's main theorem, remember when we stated that our statement from yesterday was, let me say this exactly correctly. If Q is the midpoint of points P and R, then sigma sub Q times sigma of P is equal to tau sub P comma R is equal to sigma sub R times sigma of Q. Right, so we need a midpoint between two points to apply that main theorem from yesterday, which is why we introduced the notation for M. Okay, so that we can express tau as a particular product of half terms. Tau of A sub A comma B. Tau sub A comma B. Right, so by the main theorem from yesterday, we have tau sub A comma B is equal to sigma sub M, sigma sub A. Right? Okay. So we also know that if we multiply D on the left, sigma sub D on the left to this equation, well, I have a product of 3 half terms. That means this must also be a half term, right? Is equal to sigma sub Y for some point Y. Okay? So, now, let me just multiply both sides of this equation by sigma sub D inverse, which is just sigma sub D, right? Since half terms are involutions. Okay? So this implies we have sigma sub D, sigma sub D, sigma sub M, sigma sub A is just equal to sigma sub M, sigma sub A is equal to sigma sub D times sigma sub Y. And we already have from our yesterday's theorem that this is equal to tau of A comma B. Okay, so for some point Y, I should say unique, right? So our point C is this unique Y. Okay? So I guess it's perhaps a little confusing that I use another variable there, but a priori we don't know what that point is. But now I'm saying by fiat, it's C. It's the thing that makes this equation hold. This last line, this last equality. Okay? Okay, so one more case. Yeah, time not too good today. Okay, so assume now we know A, B, and C, and consider sigma sub m, sigma sub a. Now I multiply on the right.
Should those be reversed? I'm confused.
I'm sorry.
Our equation has C on the left, right?
No, I think this is. Oh, you're right. I think.
So this is not interesting names of the variables.
Yeah, yeah, you're right. I screwed that up. So,
Would you switching C and D?
right. I think maybe it's better to. Okay, so let me think about this for a second. Yeah, I'll have to erase all these D's and put C's in. Yeah, thank you. Okay, that's all fine.
We know C.
C, yeah.
And the only other one left is on the top line of the side. In front of it.
Yeah, good. Okay, sorry about that. Well, and now we'll multiply on the right. Okay? So, and we'll set this equal to sigma c. And then just multiply by sigma d inverse both sides. Okay? And then I'll just say, and use the same argument as above with right multiplication. There you have it. Thank you for keeping me honest. Okay. So, let me ask you a question. What are the conditions on the fixed points of two half turns that guarantee those half turns commute? So let me rephrase that. Say we take two half turns, sigma sub p and sigma sub q. What conditions on p and q can I state that guarantee sigma sub p times sigma sub q is equal to sigma sub q times sigma sub p? Or what conditions on points P and Q do we have sigma sub P, sigma sub Q is equal to sigma sub Q, sigma sub P?
just trivially they're the same.
Yeah, if they're the same, they definitely commute, right?
I don't think they commute in any other case.
Why is that?
Well, I just did that analytically real quick, and you get, like, if you just look at the x coordinate, if you perform both transformations, you get one, it's like x plus 2a minus 2c, another you get x minus 2a plus 2c, and you get a equals c, so the x value on the points has to be the same, and the same happens for the y.
Yeah, great. That's pretty much the whole justification. And this also makes some kind of intuitive sense, right? If you take the plane, right? If I take my plane and I rotate about this point, and then rotate about this point, then that's not going to be the same as if I rotated about this point, and then this point, right? So, good. Let's just say that. We must have P equal to Q. Right? So. Right. Here's something slightly less trivial. Sigma sub r times sigma sub q times sigma sub p is equal to sigma sub p times sigma sub q times sigma sub r. For any points P, Q, and R. Okay, so not as nice as commutativity, but an interesting and sometimes useful property nonetheless. Okay? So, how do we begin? Well, before anybody starts to do anything analytically, what can I say about, say, the left-hand side of this?
It's a half term.
It's a half turn, right? Because it's a product of an odd number of half turns. Okay? So, sigma r, sigma q, sigma p is equal to sigma s, or some point s.
Oh, it's the same 3 points.
Sorry?
The same 3 points.
I'm not sure what. On the left and right, these are the
Yes.
same 3 points. Yeah.
Yes.
Okay. Good. For some point s, capital S, since an odd number of half turns. Okay, great. Now let's just invert both sides of this equation. Okay, so I'll take the inverse of s, I'm sorry, sigma sub s, which is what? Sigma sub s, yeah, because all half turns are involutions, right? Is equal to the inverse of this product. Now,
The inverse of each individual one backwards.
right, remember we had this, we proved this when we talked that day about group theory. The inverse of a product is the product of the inverses in reverse order. So in other words, this is equal to the inverse of sigma sub p times the inverse of sigma sub q times the inverse of sigma sub r. Now, we know explicitly what each of these inverses is because, as we just said, all half turns are involutions. So they are their own inverses. I got sigma sub p, sigma sub q, sigma sub r. Okay, so that is undeniably faster than computing analytically, having to label 3, possibly 4 points, depending on.
The same parallelogram.
Sorry,
They also make the same parallelogram, so the same points.
for any points.
Right, if they were non.
If they're non-distinct,
Right.
then you can't say that. Or if they're all collinear, you also can't say that. But yeah. Right. If you say non-collinear distinct points, then yeah, you're right. Okay, good. So I think we have just enough time for, oh, sorry. So Keenan asks, so is this just true for any odd number of half-turn multiplication, where an odd number of half-turns being multiplied together is equivalent to the reverse order of the same half-turns being multiplied? Good question. So in other words, if we had 5 or 7 or 9, I'll ask you to do that tonight on your own. So, homework. Prove or disprove.
The alternative would just be to do the inverse instead, right? For evens.
Well, write that out, and let's talk about it tomorrow. Okay, so prove or disprove. If we have sigma p1 times sigma p2, p2, all the way up to sigma sub pn, then this must be equal to sigma pn, sigma sub p sub n minus 1, all the way down to sigma sub p2, sigma sub p1, whenever n is odd. Okay, great question, Keenan. I'm excited to hear what everyone has to say about that. Okay, so I think we have just enough time to state our final result for the day, which I told you at the beginning of lecture is just that the group generated by half-turns is just the union of half-turns and translations. Okay. So, as we discussed, note, half-turns do not form a group. And why is that? Well, there's a couple of reasons, at least a couple. Namely, is iota a half-turn? No.
Full turn.
Correct. That's a full turn, or a 0 turn, a no turn. Furthermore, there are no translations that are half-turns. So if we take the product of two half-turns, we immediately get out of the set of half-turns. Right? Okay? So, however, recall that we can generate a translation group from any subset of the group. I'm sorry. You can generate a a transformation group from any subset of the group of all transformations. Right? This is, think back to when we discussed a cyclic group. We took a single transformation. Obviously that transformation alone, the singleton set, is not a group unless it's iota. But we can generate a group by taking all the powers of that until we get back to iota. Or perhaps we'll never get back to iota. That just means it's an infinite group. Okay? So we can do similar with an arbitrary set of transformations. Okay. The union of all translations and all half terms forms a group. Which we denote script H. Called the group generated by half terms. Okay. So. Yeah. 2 minutes. I think we'll just discuss the proof tomorrow. Just because I don't want to barely start and then stop. So yeah, expect those solutions for practice exam A early this evening, and then I'll also send out, hope to be able to send out a second practice exam, depending on whether I get an email response. But yeah, and then homework for tomorrow, just look at the practice exam material and then we'll go over any questions at the beginning of class. Okay, oh yeah, and of course, this homework assignment for fun.
And 3.5, right?
Oh yeah, sure, you should look at 3.5. I forgot that I told you to postpone that, but now you have all the tools to adequately address question 3.5. Okay, good. See you all tomorrow.
Thank you.
Yeah,
Thank you, have a nice day.
you too.
Thanks for
No problem, see you.
Yeah.